Hello everyone, slightly different look today. I'm trying out a new app to record videos. So today we're going to look at, where is it, there, something called a parsec. The different distances to look at, but you've probably heard of light years and you've probably heard of astronomical units. So the new one today is the parsec in addition. We'll then look at the idea of something called a stellar parallax. Now, you will have heard about a parallax with a parallax angle, the idea that if you shut one eye and point somewhere and then flip to the other eye, the angle has changed or you're no longer looking at the same object. And there's also an equation for this thing called parallax, and that's what we'll look at today. So I'm going to say goodbye in that my video is going to disappear and we'll go back to the normal teaching. But for now, enjoy. So top right, we've got the specification comments or specification points that we need to make sure that we follow today. And that's what I outlined on the previous page. So if we start with the Earth, so hopefully you recognise it, and then of course our local star, the Sun. Now on average, it's about 150 million kilometres away. Now the Earth doesn't follow an exact circle as it orbits the Sun. It is slightly elliptical. However, 150 million kilometres is a good approximation. Now, in physics, we tend to make numbers a bit smaller to make them a little bit more manageable to use. And the shortcut here is the astronomical unit. So we would say that the 1 AU is the average distance from the Sun to the Earth. And we can use that then to compare the distances of other planets in our solar system. So 1 AU is roughly 150 million kilometres. When we go slightly further, so outside of our solar system, then we tend to use the word light year, and that you should be aware, but that's the distance that light travels in 1 year. And you can work that out because you know how many seconds are in a year, and you know that light travels at 300 million meters every second, so speed, distance, time. Now, another little fact is it takes roughly 8 minutes for the light from our Sun to reach the Earth. So if the Sun does explode, we'll know about it about 8.5 minutes later. But if we want to maybe go to another star, Alpha Centauri, then that's about 4.4 light years away. So it takes light 4.4 years to reach us before we then notice it. And light years can be really useful, but then when we start looking at other galaxies, 2.5 million light years away, the numbers are starting to get large again. And what we then will use is another unit, and that one is called the parsec. Because the parsec is a new term, I would strongly recommend looking on the internet and finding some good YouTube videos to maybe explain it. But it's something that we do need to use, and you do need to be able to convert from parsecs into light years into meters again. And the numbers that you need to use are given to you in the exam when you look at the data booklet. So if we look at the triangle just here, you'll see, again, this has just been changed around so that we've still got the Earth at 1 AU. And what we're trying to do is create a right-angled triangle. So if we're looking at a distant star and we want to find out how far away it is, we can use trigonometry. And what we would say is that we've got a distance here, got a distance here, but we know this distance. And the trick is to find the angle just here, which we'll go through shortly. What I would say is on your calculator, we no longer measure in degrees. We use a slightly smaller angle, and that then is called the arc second. When that angle is a particular angle, and that's on the next page, that then gives us a distance of 1 parsec. So 1 AU, 1 parsec, and a certain angle. So let's look at that. Memory, that's what we had just there as well. So our definition of a parsec is the distance at which a radius of 1 AU subtends an angle of 1 arc second. So here we now have an angle of 1 arc second. We've then got a distance of 1 parsec, and we've got a distance of 1 AU. So it's useful at this point to think back to the previous diagram so we can start putting in some numbers and looking at the trigonometry. So I've just added the 3 bits in. So we've forced a right angle just there. We've got our angle just here. So if we start labelling this, we've got the hypotenuse, we've got the adjacent, and we've got the opposite. So using tan equals opposite over adjacent, we've got tan theta equals 1 AU over 1 parsec. Now at this stage, I don't know if you've done the small angle approximation, but given that this angle, and more on that in a second, is so small, tan theta can actually just be written as theta. So you'll see the small angle approximation, or take a look on Google, small angle approximation. So we've got 1 AU over 1 parsec. Now, as you'll see, this is starting to get quite tricky, potentially, but do bear with me. But let's look at this again in a bit more detail, but let's add in the idea of finding out what on earth this arc second is. So it's really useful to think of the idea of a clock, and a clock has 60 seconds, and then within each second is 60 minutes. Now, because of the distances that are so large between our sun and a distant star, this angle has got to be really, really small. In other words, it's a lot less than 1 degree. Now, what I've written up here is the idea that 1 degree is equal to 60 arc minutes. But then, in 1 arc minute, there are 60 arc seconds. So just the same idea as a clock. So there are 3,600 arc seconds in 1 degree. Or each arc second is really, really small of an angle. So we'll look at the idea of how to convert a little bit later. But for now, in 1 degree, we need to get into the habit of being able to split it into even smaller chunks, and that's based around a clock of 3,660 times 60. So now, if this angle here is 1 over 3,600 of a degree, that's just equal to 1 arc second, and you do that with 1 dash dash. Just in case you're reading around, so 1 dash dash means arc seconds, 1 dash means arc minutes. So in some books you might see 1 dash and that's 1 arc minute, but generally speaking you'll see 1 dash dash, which is then 1 arc second, which is an angle 1 over 3,600 degrees. So if that is the case, and the distance from the Earth to the Sun is 1 AU, which it is, then that means the distance from here to here is 1 parsec. So it's forced. We've made that as a distance based around the angle being 1. With this diagram, it's also worth mentioning about why I've written summer and winter. So when we're looking into space, we'll look at stars maybe in the summer, and we'll see that it's just there. And then 6 months later, because the Earth is continually moving, we'll look at the star and see it there. And by taking 2 measurements, that gives us an angle. So we'll look at that a bit more in a moment. So because someone else can explain this far better than me, let me just show you how to find another video just to watch, and then come back to mine afterwards. So go to YouTube and then type in stellar parallax, and the one that I tend to use is the third one down where it's got parallax A-level physics. Now as you can see, there are plenty of other ones to use, but this one here does go through the idea quite nicely. He uses a slightly different angle. That's just because he's taken a different angle and doing 90 minus theta. But other than that, it's a good one to watch. So strongly recommend watching that one. And once you have done, and maybe a few of the other ones as well, then come back and watch the rest of the video, please. So hopefully you've had a chance to watch that. Now, if we just look at this diagram, and apologies for it being hazy, but just to pick out the key things really from what you should have just watched. So we've got the sun at the middle, and as explained in the video, we've got to take measurements 6 months apart, so one in the summer, one in the winter. We've got our nearby star, and we always measure that with parsecs, and then we've got our parallax angle just there. And then in the background, we've got a series of further away stars that don't tend to move as much, and that's similar to this diagram at the bottom and the one in the video when he was looking at the mast in the background. So 2 different times of year, and then that will give us an angle, which would then just find part of the angle, and that would then be called our parallax angle. The best way to try all these things is with some questions. So what I'd like you to do is press pause and have a go at these questions, and then once you have given them a go, then we'll look at the answers. You'll see on the left a worked example to help if you need it, which at this stage I would strongly suggest looking at it first. Okay, let's just go through the first one. So given these angles, calculate the distance to the object in the specified unit. So 0.0420 arc seconds in parsecs. So we always start with the equation. So d equals 1 over p. And it's really important to know what p is and what d is, as in what the letters stand for, because it can be confusing. Although, because the equation is d is 1 over p and then p is 1 over d, it's not the end of the world if you don't. But as it says, the parallax angle is p. And because that's in arc seconds, and it always has to be in arc seconds, this equation does only work when the parallax angle is in arc seconds. And d is our distance. And again, this has to be in parsecs for this equation to work. So you may have to convert into arc seconds, or you may have to convert into parsecs, but for now, we don't need to. So we've got 0.042 arc seconds in parsecs. So what we need to do is cheat. So we've got the answers now in front of me. So we've got the 1 over p. We've then got the parallax being that really tiny number, but in arc seconds. And that then gives us a distance in parsecs. And it's given to 3 significant figures, just because we've got 3 significant figures just there. Okay, on to part B. Part B is the same idea, apart from this time we want our final answer in meters. So again, we start with the equation, d equals 1 over p. So the distance in parsecs equals 1 over 0.0317. And then again, I'll cheat by putting the answers in front of us. So then by putting that into a calculator, we get the 31.545741. Now, because that's still in parsecs and we need to convert that into meters, by using our data sheet, we can see that 1 parsec is the same as 3.1 times 10 to the power of 16. And that then turns into 9.78 times 10 to the 17 meters. So then let's just look at part C. So this time they want it in light years, but again, similar idea. So d equals 1 over p, where d is our distance and p is our angle, our parallax angle, 1 over 0.735, which gives us 1.36 parsecs. And then to convert that into light years, first of all, I suggest you turn it into meters by multiplying by 1.3 times 10 to the 16. So that gives you the total number of meters. And then light years, the whole point of light years is to have a smaller number. So you can then divide that through by 9.46 times 10 to the 15, which is, of course, the distance that light travels in 1 year in meters. So then our final answer to three significant figures, 4.46 LY, or light years. So just as a quick recap before I set you off on a few questions, we have now looked at the idea of the parsec. So that's a new distance, but the parsec is then dependent on two other things, and that is the 1 AU, the distance between the Earth and our Sun, and this angle here being 1 arc second, where 1 arc second is the same as 1 divided by 3,600 degrees. And then with the small angle approximation, we can then just say that angle equals 1 AU over 1 PC. And then we can say that the angle is our parallax angle, so that gives us a P. The 1 AU, well, that's always just the value of 1. And then with parsecs, we can then write D for distance, because that's the thing that's going to change. So that's where our equation comes from. 1 is our constant, because 1 AU is always the same, and as long as distance is in parsecs and the angle is in arc seconds, then that equation can be used. Just as a couple of more examples, we said that theta is opposite over adjacent. Our angle is just here, so a half equals opposite, which is 1, and our adjacent gives us 2. So half equals half. Likewise with this one, we've still got 1 AU, but this time our star is a lot further away. It's 4 parsecs, so consequently the angle would be a quarter of an arc second. So let's just double check. So tan theta, small angle approximation, goes to theta. Opposite is 1 AU, and adjacent, our distance is a quarter. So theta equals a quarter. So for extra work to have a look at, obviously read around the subject, goes without saying, and I've also got the summary questions on here for you to have a look at, so please have a go at the summary questions on 20.1. I've also got you some reading to do as well, so I'll get that scanned in and sent to you to have a little read about. In this one we've got another example there, and then a couple of practice questions there too. So that should be enough for now. As ever, if you have any questions, get back to me. Stay well.